Hi everybody, welcome back to Chem 140. You know what's interesting? I never thought about doing this before, but I realized that oops, hold on. Things are changing in the background on my window here. YouTube, stop it. There we go, okay. I never realized this before, and I feel really stupid, but with all this blank space in the chat, maybe we could do something better with it. Oh, wait, hold on. What happened here? I messed up. Hold on. God damn it. Just a second. Sorry. I had this sound effect queued specifically for this reason. There we go. So let me hit this. And I did this for my previous class, and I have no idea why I didn't think to do this before. But we should just have a calculator on the screen. Why not? What better use is there for this space? And we're going to be using a calculator today, so there you go. If you've ever wondered what I've been typing into the calculator, wonder no more. I'll just do it on the screen. Why not, right? That seems like such an easy solution. So there we go. We have a calculator. All right. It's great that I realized this on the last day of classes. No, we're going to do this on the first day of classes next quarter. But there you go. So what do we have to do today? We have to finish chapter 16. There's not really that much left to do, believe it or not. As far as activities that are required of you, you need to turn in quiz number 8. It is due tonight. Make sure to get that in before the deadline, because once it's closed for good. Quiz number 9 is just open. I think I have that all set up, so quiz number 9 should be available. You could take that before or after the exam. It's up to you. It's only worth 1 point, so the purpose of that quiz is for you to just use it to review. That's really all that it's for. So look at those, do the questions, see if you understand them, check your answers against the correct answers, and then ask me any questions you might have. So finally, exam number 2, Friday this week. We're going to have a review session tomorrow for tomorrow's quote-unquote lecture is just review questions, because there's not going to be any more content. We're going to finish it today. So, all right. We're going to define concentrations of solutions with numbers. And so we're going to use these terms that I'm going to have on the screen here, concentrated versus dilute. These are going to be relative terms. Something is concentrated if there's a lot of solute in its space. Something is dilute if it is less concentrated. And the intent is that you can add water to something to do the verb diluting. So on the screen here, you can see that on the left diagram, I have a lot more solute, the solute being these blue blobs. These are all my solute particles, so doot. And then on the right, I've added water, so I have increased the space between all of the solute particles so that there is less solute per unit volume. So if I took a volume, which would be this square, the concentration would be how much stuff is in the same amount of volume in the solution. Now, the volume that we're going to use is going to be a liter. And the units that we're going to use for concentration are called moles. So, well, you know what moles are. So, the units related in this manner give us this new unit called molarity. If I count the number of moles of solute in 1 liter of solution, I will get its molarity. Now, you don't need to do specifically 1 liter. So if I have a box here, and this volume of this box is 1 liter, and I put in 1 mole of stuff, and it's about this concentrated, we'll just say. So we'll say 1 mole in this box. We could say that this would represent 1 mole per liter. But if I took a smaller volume of it, so say this volume right here, the concentration is still the same regardless of the volume that I took, because the number of particles in any given space will have the same density, we'll call it. So molarity is kind of like a density, except instead of having mass per liter, we have a count per liter. And regardless of which chunk I take of this, the molarity will be the same. Now, the number of moles will be different, and the number of volume will be different for the amount that I select, but the ratio of those two will always remain the same for this 1 molar solution that I've made. Now, very important, on the bottom here, this term right here, this is solution and it is not solvent. So if you add a mass of solute and then you add a liter of water, your total volume will actually be larger than a liter because the solute adds a little bit of volume, right? It occupies space too. So be mindful of that. You want the volume of the solution. You're not going to measure out how much solvent you put in. You're going to just measure out whatever the end volume ends up being. So let's do a sample calculation here. I want to make 1.75 liters of solution. So I add 2 moles of calcium chloride to the container, and I add enough water so I fill it up to the line. What would its molarity be? So the way that we would do that is we would say, okay, well, the moles of solute would just be 2 moles. That should have been an A. And then the volume would be 1.75 liters of solution. And I ran out of space. We're going to go down there. Now I have to actually go get the calculator out. So we go 2 over 1.75. Boop. There you go. Way too many sig figs windows, but that's okay. So I can write that like this. I have that many moles of calcium chloride per liter. Or I could write it like this. 1.14 capital M CaCl2. Where the capital M is just the moles per liter. All right. So that's our basic calculation for molarity. Because molarity is a conversion factor, we're going to be using it as that later today. But now you know how to do a very simple calculation. Now, what are going to be our uses for molarity? It's going to be very practical to work with molarity because, again, we work with a lot of liquid solutions. We don't really do chemistry in the solid phase or the gas phase in early classes. You can do them like that, but it's harder to explain what's going on in an introductory level. With solutions, it's very straightforward. Everything can contact everything else. It's very straightforward for things to react. We don't have to worry about pressure. We don't really have to worry about temperature. We just have to worry about number and then volume. So 2 variables as opposed to 4. That all being said, how do we make solutions so that it's practical and useful to us? Like, what's our procedure here? I can't just give you 14 molar HCl and say, yeah, use the right amount. That's too dangerous and also prone to error. So let's make solutions that meet our specifications and then use that from stock solutions that we have kept in the back room where I can prepare the solution and then give you what you need. So let's suppose I wanted to make a 1 molar solution of sodium chloride, and I give you the following things. I give you a 1 liter flask. I give you infinite solid sodium chloride. And I give you infinite water. Now, obviously not infinite water or sodium chloride, because that's not a real thing, but I give you far more than you would ever need to make this solution. What would you do with these components? How would you do this process? So let's talk about a procedure here. This didn't show up. That's weird. Oh, there we go. Okay. Scroll all the way up here. You see, I put the calculator on this page too. All right, so if I want to put... Here's my sodium chloride on like a little sheet, a little weighing boat or something. We're going to put this in a flask with volume 1 liter. I only get 2 sig figs for that, but that's okay. We'll just erase. So how much do I weigh out? Well, let's do a calculation here. So molarity equals moles solute over liters of solution. And I know I want a 1 molar solution, and I have a 1 liter flask. So I could calculate this in a rather straightforward manner. I would just say molarity times the volume equals the moles of solute. Right? We could do that. Now, this is going to be very straightforward because I want 1 mole per liter, and I have 1 liter. So the liters are going to cancel out, and I just get that. Don't even need to use the calculator I set up for that, right? So this is the amount of NaCl that I would need to put into the container, because I know what molarity I want, and I know what volume I want to make. Then it's just a matter of saying, okay, what exactly is 1 mole of sodium chloride? Well, if I do this, we can turn it into a mass, and I actually know what this is. I believe, anyway. So 23 and 35 is 58. That's right. Okay. I only get 2 sig figs, though. So there you go. So we have now figured out what amount of sodium chloride goes into the container here. And so what we're going to do is we're going to say, okay, well, this is going to be 58 grams of sodium chloride. So what I'm going to do is I'm going to pour that into this container, and so it's going to be in here now. And then I'm going to add enough H2O to fill this all up so that it goes up to the fill line. And then your solution will be 1 molar, provided that it's homogeneous. So let's write down what we just did in a series of 3 steps. We're going to prepare a solution. Step 1, weigh out the amount of sodium chloride you need. We'll call that the solid. We're going to add to the flask. To do that, you need to do the calculation that we did right here. Then we're going to add H2O until it hits the fill line. And then we need the solution to be homogeneous, so we're going to mix it really well. Let me try that again. Generally speaking, 1 minute of sitting there with your thumb over the lid of the bottle, holding it shut, and then just inverting it for 60 seconds will be sufficient. In fact, experiments have been done on this where they did no mixing at all and then tested different samples of it to see how homogeneous it was. And it was found that after 60 seconds, you're good. So you just sit there and flip it upside down for about a minute. And then finally, there is a 4th secret step. Enjoy. All right, so that's how we make any solution when you have a solid reagent. We're going to talk about how to do liquid reagents in just a little bit. So on the screen here, I have this all drawn out a little bit better. That disappeared. That's not what I wanted. I wanted to zoom in. There we go. Back and forth or just hold it upside down. So invert it over and over and over. So flip it upside down and then write it back upright. The reason for that is because in this little head, you can see right here actually, in this little head space, when you flip it over, that's going to bubble up down to here and be down here. And then when you flip it right side up, it's going to bubble back up to where it was. And this action of this air bubble moving back and forth mixes the solution. All right, so on the screen is what this looks like using actual equipment that is drawn by somebody who actually knows how to draw lab equipment. I do want to point out some things, and unfortunately to do that I had to zoom out because it won't let me draw real quick there, or real close there. Any container that you put stuff in runs the risk of not transferring completely. So for example, right here you can see the salt. Some of the salt might get stuck to the sides of the container. So when you're adding water, the first thing that you want to do is you want to rinse both the container it was in and the funnel with your water. That way you'll be almost certain that you get all of the salt in there. Much less will remain because the water that you squirt in there with the squirt bottle will rinse by gravity into the funnel and then into your solution. As long as you don't do more than a liter's worth of this water, you'll be okay. Then once you've done that, once you've rinsed all of this out really well, you can then fill the remainder with water until you hit this line. Now the line is actually rather important. We're going to zoom this in over here. So the way that you want to fill a solution on the fill line is that you want your water to touch the fill line. Now, unfortunately, water does this sort of thing. This is called a meniscus. A meniscus is the result of water being attracted to the glass because we said yesterday water was polar. Turns out that glassware contains oxygen and silicon atoms, which create a polar arrangement. So water is attracted to them and actually climbs up the sides of the glass. This is called capillary action, if you've heard of it, or adhesion. As a result, it's hard to make water land straight on the line. So what we want is, this is what you want. You want your water meniscus to sit on the top of the line, like that. This would be great. I have exaggerated this a little bit. Like, it's not going to be that curvy, but you want it to touch the top of the line. If you are too low, add more water. But if you go too high, cue the Price is Right losing horn. If you go too high above the solution, you have to start over. And the reason for this is because your solute is going to be down here, right? This is all your sodium chloride. But as you fill this up, it gets up here too. You can't just remove this part because you'd be removing solute, right? You have made it too dilute, and then by dumping out a portion of that, the concentration doesn't go back to what it was because you're not removing just water, you're removing solute as well. So make sure that when you're preparing these solutions, if you have an instruction next quarter that is in person, I'm not sure if 161 is in person for anybody, but in the fall it will be. If you are in that circumstance, be very careful you don't overfill. If you overfill, your solution is wasted, and then you have to start over. Okay, so be very careful with this. And then, of course, at the end, make sure you mix. Mixing is actually the most crucial part. It's the part that people will forget to do because it's like, oh, whatever. You don't really think about that. And then when you go and use your solution, you'll realize that, oh, all of these aren't the same thing. They aren't all identical, and I'm getting different results. And that's no good, right? We want our science to be reproducible. And the way to do that is to ensure that all of the portions of your solution are the same. So actually do the mixing. Sit there for a minute and do it. I know it sucks, but you can talk to me in the lab or your instructor or whatever. In fact, if you talk to the instructors during the lab, we like that because we're just sitting there grading papers or watching you, I don't know, drop shit or whatever. And it's nice to have a conversation with people. So the lab is a great time to interact with the instructor while you're doing menial shit like flipping up solution, right? All right. So what I want you to do now is I want you to tell me how to make this solution here. I want, instead of 1 molar solution of NaCl, I want 3.50 molar KBr. I still want a liter. I want you to tell me how much you want to put in the flask, and then draw out a procedure using the 3-step plan that I showed you over here for this specific solution. Try to use numbers to describe your plan. So, like, if you weigh out an amount, say, I'm going to add 11 grams of whatever to this thing, and then I'll add this much water to fill it up and mix, or whatever. So, try to be as specific as you can so that if you gave me this procedure, I could look at it and go, yep, I can do that, and I'll go make it for you. Okay? I'm going to give you about 5 or 6 minutes to do this, then we'll go over the answer together. So, see you in a bit. All right, one more minute. We'll go over the answer. All right, so let's set this up here. All right, so we'll do that first, and then I'll change what I have shown on the screen here. So I need this solution. So molarity equals moles of solute over liters of solution. And so to get to the number of moles of solute, I'm just going to multiply this over here. So that's going to be molarity, times volume, or the liters of the solution. And that will equal the moles of solute, which would be 3.50 moles per liter times 1 liter. So that would be 3.50 moles of KBr. So that's what I need to add to the flask. But it's much easier to work in a mass, so we're going to do that. And I don't have any idea what KBr weighs, so I had to look this one up. KBr, 119. And then we can go 3.50 times 119, 416.5, so we'll round that to 3 sig figs. And there you go. So now that we've done this, we can do our 3-step plan, which is up here. We'll just write it again. That's fine. So step 1, add 417 grams KBr to a, not to at, to a 1 liter flask. And then step 2 is add H2O to the fill line. And then step 3, mix for 60 seconds and enjoy. Or question mark, profit. That works too. I just want to do it in 4 steps. Actually, I don't care about profit. I care about I'm a hedonist. Like, it's all about enjoyment, right? All right, there you go. Good, you can make solutions. Hooray! Let's do more calculations with this, because this is where we're going to go. That molarity times volume thing is very, very practical. So we're going to shorthand this instead to this. So molarity being capital M, and V being volume, multiplying those together will give you moles. And you could do this for any practical application you want to. The important thing to note is that you have to have volume in liters to do this. And the reason for that is because molarity is in moles per liter. And if you don't have it in liters, the liters won't cancel out. You can't see that because my big ugly face is in the way. Hold on. So let me just delete me. Boop, there we go. We don't need me there. All right, so those units are going to be very relevant for this equation because we need to actually cancel out units. So here I have half a liter, 500 milliliters of 0.350 molar magnesium hydroxide. So if I wanted to figure out how many moles there were, I would say the molarity is 0.350 moles per liter times, and I want 500 milliliters in liters. So I'm going to change that. I'm going to do that. There you go. So again, make sure you convert all your volumes to liters when you're using molarity, because otherwise you're going to get an answer that's like 1,000 times too big. All right. But we can erase that now. And then I can put my face back. Yay! All right. So I'm going to give you these two problems that are going to use this concept, and then from there you can do other calculations that we've done in the class so far. So all the Unit 13 and 14 and 15 stuff is going to come back to haunt us here. So the top question, I have 35 milliliters of 2.50 molar HCl. Tell me how many moles of HCl are in the beaker, and then how many grams of it are in the beaker. Down below, the problem is much more interesting. If I give you 3 molar potassium dichromate, and I give you 250 milliliters of that, you can tell me how many grams of potassium chromate are in the sample. And if you know how many grams are in there, you can tell me the mass of just what's of chromium, right? Because you could do mass percentage, or you could turn grams to moles to grams. So both of those questions are interesting and doable now. So I'm going to have you do them. So I'm going to give you about 6 or 7 minutes to do all 4 of these questions. Do as many as you can. And when time is up, we'll go over the answers. And we'll keep going. So see you in a bit. Let's do 1 or 2 more minutes, and then we'll go over the answers. All right, let's go over the answers here. So we'll go boop, and everything's gone. All right, so I have 35 milliliters of 2.50 molar HCl. So first thing I want to do is I want to turn this into a volume. So that when I do m times v equals moles, that my units will cancel out. So I have 2.50 moles per liter times point, oops, 0 in there, 0.350 liters. And so those would cancel out. So how many moles of HCl would I have? So let's see here. So 2.50 times 0.0350. And I get 3 sig figs, so I get 0.0875 moles HCl. So there's the answer to number 1 right there. And then if I want the answer to number 2, I could just do moles HCl, 2 grams HCl. And 1 mole is how much? Let's see here. Where is Lentech? I gotta find it. HCl, 36.46. So we'll do 0.0875 times 36.46 equals 3.19 grams HCl. So that's number 2. There you go. All right, for the second problem, well, I guess 3 and 4 here. So I have 250 milliliters of solution and 3 molar potassium dichromate. So immediately, again, I'm going to do this to it. Well, I'm going to do that to it. So I have the right number of sig figs. It won't matter because this only has 3, but I don't want to make a mistake on there. So, and then again, m times v equals moles. So molarity, 3 moles per liter times the volume, 0.250 liters, equals So clear 3. So that's not a 3. 0.750 moles of K2Cr2O7. And I need a mass for that, so we're going to go 1 mole potassium dichromate. That one I definitely don't know. I'm going to look that up immediately. K2Cr2O7. I got 294.18. I typed the wrong thing. Hold on. Why didn't that work? That's what I want. I want 220.635. Okay. Or 221 grams K2Cr2O7. So there's number 3. And then for number 4, we can actually work from right here. So if we have this many moles of K2Cr2O7, I could say that for every mole of K2Cr2O7 I have 2 moles of chromium in it, right? Because part of the small thing is part of the big thing. And one of the big thing, there are 2 of the small thing due to this number right there. And then I could say, okay, well, moles, chromium, grams of chromium. In a mole, there are, periodic table, 51.996. You know, that's close enough to 52. We'll just do that. So now I can go to the calculator and go, not F1, there we go. 0.750 times 2 times 52.00. And I got exactly 78. Look at that. And that's the answer to number 4. There you go. So those are the types of calculations that we can do with molarity and volume together. It just links to all the stuff that we've been doing so far. So really, we have the foundation of all the calculations that we need for like Chem 162 and 161. And now it's just a matter of like making extra connectors. So like you have the core calculation of like turn grams into moles or moles into particles. And now it's just what are other ways to get to moles, right? Because every time we learn a new way to moles, we can link different concepts together and then come back to this general concept of figuring out calculations with mass and moles and volume. I gotta click here. Actually, no, we're due for a break, so I'm gonna just put this on the. Let's see here. We've already done these examples, so it's just more of the same. So I'm gonna just leave those for you to practice, and put the marker here so that when we come back to after the break, we can talk about dilutions. So I'll start the timer. We'll get the music going again, and I'll see. Oops, sorry, I clicked the wrong thing. I'm muting myself. I'll see you in about 10 minutes. Hi everybody, we're back. Let me wind this back down here. Okay. So, let's do the last two sections. So, dilutions are a procedure. Let me start over. So, diluting things is a laboratory procedure that you can follow to take concentrated solutions and turn them into solutions that have a lower molarity of your choosing. Generally speaking, we don't want to ship out dilute solutions because you'd be shipping water, and water is abundant, relatively speaking. So, like, you can turn on the faucet and get water, or you can get distilled water from, like, a specific supplier that's local or whatever. Shipping heavy things like water, not super practical. So, if I'm going to send you a solution of HCl, I'm going to send it to you as concentrated as possible, so that I'm shipping the most solute and not water. If you need to dilute it, you could provide your own water. That's something that you can do on site. So the act of diluting is very practical for not just a logistics perspective, but also from a science perspective, because who knows what we're going to need, right? Like, I might need 1 molar HCl for one experiment, but the next experiment, 1 molar is too concentrated. I need 0.1 molar. So buying 75 different bottles of solutions is not very practical. And it's also cumbersome to deal with in the laboratory, so let's just prepare solutions. And we can do that very easily in the following manner. Any solution that's concentrated, you can add water to it and dilute it. And the way that we do this is we use this formula. This is a very simple formula, but very, very important. This formula works only for dilutions. Do not use it anywhere else. You will be tempted to, and you'll get whatever you're working on wrong. So don't do it. Only use this for dilutions. So check your problem, make sure that the question is asking you to dilute something, and then you'll apply this formula. That was a terrible straight line, but that's okay. The S side is the stock side of the equation. Or what you have in the stock room. This is the stuff that we just have lying in the back in the closet that we're going to use to prepare any solution we want to. The D is the dilute side, and this is what you want to make. And you could choose whatever you want to make, because it doesn't exist yet, right? So we're going to prepare it to these specifications. I want this molarity and this volume. M is molarity and V is volume, and generally speaking, these three numbers are fixed. This one is just on the stock bottle. And then these two are of your choosing. So that means that most of the time you'll be solving for this variable using this expression. Now, practically speaking, M times V is still moles, and M times V is still moles. So what we're ending up here is really just an expression that says moles equals moles. But that kind of checks out, right? Because the moles of the solute that are in here, before and after, are not going to change. The only thing that we're really doing is we are creating a new molarity in volume by adding water, right? So the number of moles of solute before and after the process of dilution won't be altered at all. So when you look at this expression, yes, you are going to get something equals itself if you're thinking in terms of moles. But remember, if you're only adding water, the number of moles is not changing. So that's good. This lists all of the variables. I think that we've already done that more or less. So let's take a crack at one of the problems here and see how we prepare the solution. So we're going to go over to this screen here. And there's absolutely nothing here because I've captured the wrong thing. There we go. Ah, there we go. All right, so I have 10 molar calcium chloride in the stockroom, and I want 3 liters of 0.5 molar calcium chloride. Whenever I'm given a dilution problem, here's what I do. I say, okay, I want molarity and volume, and then I want stock and dilute. I'm going to just make this little kind of coordinate grid where I'm going to put whatever the stock molarity is and the dilute molarity in this box, stock volume, dilute volume. We'll just fill in the grid like that, right? Where's my history tab? There it is. I went back too far. Hold on. There we go. All right, let's look at the numbers that we have. So I have 10 molar calcium chloride in the stock, so I immediately know that that's this. And I want to make 3 liters of 0.5 molar calcium chloride. So I can fill in the other numbers based on the context of the problem. And then this is going to be what I solve for. So we'll just do the algebra real quick. And now we can fill in the numbers, right? So I have MD, which was 0.500 moles per liter. I have volume dilute, 3 liters. And then stock molarity, 10 moles per liter. You'll notice I didn't write moles per liter out because these are just going to cancel anyway. And what I'm left with is going to be the stock volume that I need from the stock solution. So that's 0.5 times 3 divided by 10. And I get this number in liters. Now, specifically, I get liters because those are the units that are left over. But for this expression, you can put whatever volume unit you want, because if you put this in milliliters over here, and you solve for V sub D instead, you'll get an answer in milliliters. So you can set this to whatever unit you want to, as long as they match. So they can be any unit you want. You could do cubic meters if you wanted to. Knock yourself out. All right. So now that we've got this number, what does this mean? Well, we're going to prepare a dilution. And guess what? It's the same 3 steps, right? We're going to measure the stock solution into a flask. And you need to do the calculation to figure out how much stock solution you need to measure. You're going to choose what flask you want, and that's fine. Then we're going to add H2O to the fill mark. We're going to mix for a minute, and then we're going to enjoy. So, same procedure, just a different application. All right, and then we got a picture of that on the next slide here. There we go. Again, same thing. So we're adding the liquid into here. Make sure that when you rinse, that was supposed to be an E, but it's glitching out. I don't know why. Make sure that you rinse with the squirt bottle to get all the liquid that's in there so that you get all of the concentrated stuff that you want. And then fill to the line, just like before. So your meniscus lands right on the line. Down here, you can see that it says M1V1 equals M2V2 instead of S and D. It's the same thing. The subscripts don't matter. All right, I did it. I want you to do it now. I'm going to give you 14 molar HCl because that's the good stuff. That's as concentrated as we can make it. But for the lab that I'm going to prepare for you guys, I only need 1 liter of 1 molar HCl. Tell me how much stock solution I need to measure out, and then tell me in words or pictures. Words, obviously, because you can put it in the chat. How do I make this solution? I'll give you 5 minutes to do it. Good luck. All right, one more minute. We'll go over the answers. All right. So, oops, let me do that. So I have one. Oops, let's just do this first. There we go. All right, so I've got 14 molar HCl, and I want to make 1 molar HCl. And again, I want 1 liter of it. I'm not sure why all my problems just have you make 1 liter, but if it's a different volume, you have a different number there. That's fine. So there's our expression. We can fill in the numbers now. So we've got dilute molarity was 1 mole per liter. The volume was 1 liter. Stock molarity 14 moles per liter. We'll cancel those out. And whatever 1 divided by 14 is, right? 0.0714 liters, or 71.4 milliliters. Excuse me. There's our volume. So, step 1 would be to add that of stock solution to a 1 liter flask. Step 2 would be to add water to the fill line. And then step 3, oops, I can't circle because I'm down behind my head. Mix for 60 seconds. And then step 4, enjoy. All right. You guys have the gist of this. Let's see. All right, we'll give you these 2 problems to do. Oops, I guess we won't. There they are again. All right. The first problem is a little bit trickier because I'm not asking you to solve for the volume of stock solution. Instead, I gave you the volume of stock solution here. And I want to know, what will the end volume be? So it's literally just solving for a different variable. You can swap around these. You can swap around what you're solving for by just asking a different question. So be mindful of what the question is asking. The second problem is just like all the ones you've done, except all the numbers are different. So go ahead and try these 2 problems. I'll give you about 5 or 6 minutes. We'll go over the answers after that. All right, one more minute. We'll go over the answers. All right, let's go over the answers. Oh, that lined up pretty good, actually. Okay. Let me scroll this up. All right, so for this first one, so I have a 15 molar solution, and I want to make a 3 molar solution of it. But the question is asking us, if I give you 200 milliliters of 15 molar NaOH, what would the final volume be that would make it be 3 liters? And so we could solve for that. And so that would be, so the stock molarity is 15 moles per liter. The stock volume is 0.2 liters. And the dilute molarity is 3. 15 divided by 3 is 5, times 0.2 is, oh look, it's our favorite volume to make solutions out of. Right? You don't always make 1 liter, but I mean, 1 liter is so convenient because then you don't have to do any more math. And I think when I was writing these problems, I was just taking them out of textbook preps. Like, oh yeah, we make this solution, so here you go. All right. This one, it looks like I just chose some random numbers. So I have 6 molar NaNO3. So, oops. There we go. So we're going to start with 6 moles per liter. And we're going to end with 1.20 moles per liter. And I want 525 milliliters. And you already know how to rearrange the equation by now, so I'll spare you that part. So dilute molarity, 1.20. Dilute volume, 525 milliliters, or 0.525 liters. And then stock molarity, 6 moles per liter. And that one I have to calculator. 1.20, 0.525, 6. That's not a 6, that's a 9. Either of those is fine. And there you go. All right. Any questions about dilutions? Let me know. Let's do the last section. So, stoichiometry was the whole point of chapter, 15, where we just did grams to moles to moles to grams. Here, we can do this with volume now instead, because volume times molarity equals moles. So, we can just make a new connector and then just attach that to our diagram here. So remember this diagram here? You can still use it. It's just that the connections to go between volume and moles, you're going to use molarity. And molarity is a conversion factor because it relates volume to moles. So if you're given a volume in liters and you multiply it by moles per liter, you now have moles. Likewise, if you have a number of moles and you multiply it by this, which is just molarity upside down, then you get volume. So you could just flip the molarity expression however you want to. So if you had this solution, you could write this as this, or you could write it like this. Because those are the same expression for that solution. There are this many moles per liter, and you're just setting up the unit so that you cancel out whatever you want to, which presumably would be whatever's on the bottom, right? To get to where you want to go. So that is virtually everything you need to know to do these problems. So let's go ahead and just jump right into them. So for this problem, I'm going to use 0.250 molar sodium hydroxide, but I want to know what volume I need to react completely with 4.90 grams of phosphoric acid. So I have a mass here. So we're going to start here. We'll turn it into moles. We'll turn that into moles of sodium hydroxide, and then we'll figure out what volume we need, right? So just this sort of thing. So let's do an example of that, and then we'll have you do the next one, and that's probably all we need to do, really. All right, so we've got 4.90 grams of phosphoric acid. I don't actually know if this is a solid, but whatever, right? So we've got mass, phosphoric acid. Whenever you do stoichiometry, turning stuff into moles is a great first step. And then I can turn that into moles of whatever else I want to. And then from there, I can solve the problem. So let's do that. So how many moles are, how many grams are in a mole of H3PO4? We could type that in on Lentech. And it looks like that's 98 grams per mole is the molar mass of that. Then we'll do moles of H3PO4 to moles of sodium hydroxide. Okay. How many moles of what? Well, according to the balanced chemical equation up there, for every one of these I put in, I also need to put in 3 of these. And you can get that information... Oops, I didn't click on the right thing. Right here. So this number and then this blank, which is supposed to be a 1, in the equation. Make sure your equation's balanced, otherwise you can't do that. And then finally, if I'm going to turn this into a volume, I just do moles per liter. And I don't even have to put anything up here. I just have to put whatever the molarity is next to moles. Make sure you do put the number next to moles. If you put it next to liters, then what you'd be saying is it's 0.250 liters per mole. That's not what molarity is. And then finally, we just type everything in the calculator. If I could find the calculator, it got buried under a bunch of screens here. So whenever we're doing stoichiometry, use parentheses. 4.90 times 1 times 3 divided by parentheses 98. Oops, hold on. Oh, guess what I did. $98 times 0.250. Close parentheses. There you go. And so what are the units that are left over? Well, it's going to be this, right? So I would need 0.6 liters to completely neutralize the 4.90 grams of phosphoric acid. All right. So really just like what we were doing before. So should be no problem if you have been practicing your stoichiometry from Unit 15. All right. I did one, you do one. This time I gave you calcium hydroxide and nitric acid. I want to know what volume of 0.125 molar calcium hydroxide reacts completely with 15 milliliters of 0.225 molar nitric acid. Now remember, you're not doing the dilution formula, so you can't use the dilution formula. And because you're doing molarity, to convert stuff to moles, you need the numbers in liters. So turn the milliliters into liters for your first step, and then work from there. I'll give you 5 minutes. We'll go over the answer, and then we'll put the last problems up on the screen. Let's do 1 more minute. We'll go over the answer. All right. So let me fit this all in here. Is there a 1 over there? Yeah. Okay. So for this problem, I gave you a volume to start with, which means that we are going to start with volume of nitric acid, which you can turn in the number of moles by using the molarity. Excuse me. And then once you know the number of moles, you can turn it into the moles of whatever the heck you want to at that point. And then we can turn that into a volume. Oops, whatever, that's fine. All right, so what volume do we start with? We started with 15 milliliters, which is that of HNO3. And then we'll use molarity. So moles per liter. So that would be this moles per liter of HNO3. For what it's worth, you could write liters of HNO3, but I end up putting the identity with it next to moles anyway. So I just have liters. Yeah, make sure you are writing out all your units here, because otherwise it's really easy to get lost. So how many moles of nitric acid? So it says put in 2 and also put in 1 calcium hydroxide. And again, those numbers are right here. Well, right there and then right here. And then finally, moles of calcium hydroxide per liter, and I need to look at the molarity of that. So that's 0.125 moles per liter. And this will give me the volume of calcium hydroxide, and I need the calculator. So parentheses 0.0150, 0.225, 11, so we'll do that. And then 2 times 0.125. I get 13.5 milliliters, or 0.0135 liters. Either of those is good enough for government work. Looks like everybody is doing just fine. So we'll put these last problems on the screen here. Oh, I don't know why that animated in that order, but so here's the oops, accidentally skipped ahead to the last thing. How much time do we have? We have 8 minutes left. Go ahead and do these. Yeah, I'll give you like 4 or 5 minutes. I could do them in 5 minutes. We'll go over just a little bit. Let's finish them off. Let's do it right. So I'll give you 5 minutes. Do as many of you as you can. Then we'll go over the answers, and then we'll talk about what that means for the rest. So see you in a bit. All right, one more minute. We'll go over the answers. All right. So we'll go over here. Oops. All right. So we're going to use 52 grams of iron hydroxide. Iron 3 hydroxide specifically. So we can turn that into moles pretty easily. And then we want to figure out how much HCl will react with that. So we'll go moles HCl and then volume HCl. Oops. All right, so we'll turn grams into moles. I don't know how many grams there are in a mole of this, so blend check does FeOH3 106.87. Okay, cool. And then I want to turn that into moles of HCl. So there we go. And according to the balanced chemical equation, I put one of these in, and I also put in 3 of these. And then finally, for the molarity is 1.50 moles per liter. So how many liters would be needed to react with this? I don't know why I keep reaching for my calculator. I put my phone on top of the calculator so I don't keep doing that. Like, go to the computer calculator. That's what it's for now. So 52.0 divided, or times 3 divided by 106.87 times 1 times 1.5. So almost a liter. And then how much FeCl3 will be made from the same amount? Now I'm just going to copy and paste here, because we're going to run out of time if I don't. Copy, paste. Whoop. So grams to moles of whatever other thing I want, which in this case would be FeCl3. And according to the balanced chemical equation, it's 1 for 1. And how many grams of FeCl3 are there in a mole? I don't know. 162.20? Sure. There we go. So 2.0 times 1 times 1 times 162.20 divided by 106.87. And you indeed do get 78.9 grams of FeCl3. There it is. All right. There's no more I can teach you. We've covered all the topics in the class. All that remains is to celebrate. Hooray! And that's all she wrote. That's all I have. So, here we are. We're at the end. Not much left to do. It's all on you at this point, right? So, last call for quiz number 8 is tonight. Make sure you get that in. Quiz 9, do whenever you want to. It's just for practice. Make sure you check the box in there so you get your 1 point. Exam on Friday. Final next week. We'll meet tomorrow to go over lab number 5, which is really just more practice for titrations and... Not titrations, sorry. Aqueous stoichiometry. It's all the stuff that we did today. So, I think for tomorrow's review, what we'll do is... if you have questions, we'll do them. But for like the first 30 minutes or whatever, I'll walk you through how to do parts of the lab. I don't grade lab number 5 super strictly. It's more just, did you get close? But we'll talk about that tomorrow. Yeah, that's all I got. So we'll do this thing again here. Do all those aforementioned things. Have a wonderful night. We'll see you at the review session. Bring any questions you might have. Take care.